Boom.
Boom. That's trans. This is getting pro.
We are broadcasting live on the
Whoa.
cs201 channel.
cs201.
That's right.
Welcome.
All right, so today,
Ah, we broke too soon. We
uh,
only kept it up for like 5 seconds.
you broke.
Damn.
You broke, and then I broke.
That's true. I broke, and yeah.
Back
Damn.
to
Back to.
back to this. So today we're
Yeah.
going to be discussing algorithmic complexity.
So complicated. It's complexities in the name.
We're going to try to make it simplicity though.
Yeah.
It'll feel like simplicity.
Yeah.
So, that's a good question.
So how's everything going for you? I feel like we need to start off with a couple pleasantries. How's it going?
Uh, well, I'm teaching class, and
Oh, that's
so
good.
that's going all right. We'll see how it goes by the end. If
Yeah.
it goes well, then I'll say that my life is great and everything makes me very happy. If this
I
lecture,
already have a question.
no questions.
Oh.
We're not accepting questions at this time.
Oh. Oh, okay. All right.
So, what's our goal for the day?
Get through this.
We're gonna define big O, big omega, and big theta.
Mm.
And I mean, you know that this is kind of my lecture because it involves capital Greek letters that kind of terrify people, but I really do like it. Oh, questions from students are allowed, but I was just preventing Ben from asking any questions. So, and then we're going to do some examples to show the usefulness of the ideas, and then we're going to talk about some basic ways to calculate big O, theta, and omega of any algorithm. How about that, Ben? Sound like a good
Yeah.
a
Yeah.
good set of objectives. I mean, if we can achieve these objectives, if everybody comes out of this lecture understanding this, then I would say that I should get some kind of gold star.
Yeah. I also think we want like adequate browning on the crust, but
I suppose.
yeah.
Okay, let's proceed. So, I don't know why people care about this crap. Maybe you don't. But I did a little wiki searching and I discovered that Big O was invented by Paul Bachmann and Edmund Landau. And, Landau and Bachmann were actually number theorists. So, you know, as it turns out, you can blame mathematicians for the existence of this notation.
Wow, I usually just blame mathematicians like in general for most things. So,
I know, but that's only because you know me.
oh,
Yeah, so number
yeah.
theorists, most of the time, this is actually less common in modern number theory, but yeah, you see it a lot in physics too. They do a lot of big Owen. So, anyway, and then of course, our big friend Donald Knuth wrote The Art of Programming and started popularizing Big O in computer science. So that's how it kind of ported itself into computer science. And yeah, well, computer scientists are mostly mathematicians in disguise. I would say some mathematicians are also computer scientists in disguise, but it's not bijective.
Uh,
You see, no one would be able to. Oh, you know what we have deployed? The most important thing, our groan
what?
meter.
Oh yeah, let's get the groan meter groaning.
Yeah.
Yeah, the gronometer or groan meter, gronometer. It
Uh
depends on
yeah, it depends on many things.
Let's see, have they kept the average? They've been keeping the average for it at 69 because
Well,
they're
yeah,
yeah.
because they're college students and
This is the homegrown gronometer that I wrote for funsies like Thursday night.
So
Thursday night. Anyway,
let's talk about the the mathematical definition of Big O. So I think this is. I mean, we can do some like for all blah there exists a blah such that blah blah blah, but I think that the best way to say it is f of n is big O of g of n. I guess if f of n is big O over g of n, then eventually some multiple of g is going to be bigger than f, and it's going to stay that way forever. So, yeah, we have a lag spike. Can I hear myself
I can hear you.
on the stream?
Oh, the stream.
I can't hear myself
I
there.
can hear you. I can
Okay.
hear you on the streams.
Okay, good. Yeah, let me just say that again, because I think we're back. So yeah, f of n is big O of g of n. And then we're going to be very kind of vague about what the word eventually means, and then we're just unfortunately have to say some fixed multiple of g is bigger than f, and then it stays that way forever. So f of n may not be bigger than g of n initially, but it's going to get bigger than g and stay that, or g is going to get bigger than f and then stay that way ever after. So
I'm confused. I have a question. No, I'm just kidding.
okay. Yeah, so our goal is to say that an algorithm takes O of gn of n time. Oh crap, I can't even read my own slides. So if something takes O of g of n time, then what we're basically saying is that eventually the algorithm behaves the same as the function g of n as you go off to infinity.
Or it does. Always does better than g of n. Or at
Yes.
least as well as g of n.
Sure. Yes.
And by as well we mean like faster.
Right. And of course the question is, what is n? And generally n is some kind of input size. So if your algorithm takes a list, so if it's a searching or a sorting algorithm, n is usually the length of the list. If your algorithm is some kind of string algorithm, then it'll be the length of the string usually. I mean, this can obviously vary, but let's just go with n is the size of the input that we stick into the algorithm. Okay. So we care about performance as we increase the input size, and we want the algorithm to basically track along with g of n in order to have these kind of statements. Okay. So, oh yes, and then I included this sentence. Another way to say it is that a constant times g of n is an asymptotic upper bound for f of n. So that's the worst way to say it.
Yeah, that's bad.
I mean,
it's a lot of. There's so many words there.
You see, the nice thing about it is that it's concise. The bad thing about it is that it's unintelligible for most people.
Yeah, burps are concise too. But...
Right. I think I forget. Oh no, that was when I was working at NASA. Yes, I had a debate with people. It was a weeks-long debate, and the debate was basically. They tried to tell me things, and for some reason they started believing that I wanted things as concise as possible. And I tried to explain the difference to them between like just being concise and explaining the complete idea that they have, because they were very concise. They would tell me literally 1/10 of their idea. But in a very short, very unintelligible way, and so this is my homage to that. Okay. All right. So what about big theta and big omega? So let's not even worry about that right now. Let's talk about functions. Let me find, where is it? Here it is. Here is this nice little program, or app, or whatever you want to call it. So let's discuss what BigO means in terms of the behavior of functions. So if I have, say, like y equals x, right? And I have, say, y equals x, say, squared, right? So if we zoom in on them and we look on, if we look at them on this interval, what do we see?
Get closer. Enhance.
Yes.
Enhance.
It's like the movies.
Enhance.
I'm doing it. I'm doing it. Jesus, I'm gonna turn you down. So
we gotta find this murderer, Eric. Enhance.
I know. Can you zoom in on the license plate, so that a 640 by 480 camera is now makes it legible? The answer is of course we can. Okay, so this purple function is f of x equals x. This other function is f of x equals x squared, right? And so the idea here is that, f of x is actually bigger. And I've zoomed in really, really, really far to make it look like this. F of x is actually bigger, right? And we can play the same trick if we do something like 1/10 x squared, something like that. And we see that, oh, look, we can go really far out.
Whoo-wee.
And look, this function is still bigger, right? So what that means is that the amount of time that this algorithm would take would be longer than the amount of time that this algorithm would take, right? But that's not really what BigO is talking about. So this is where the eventually part comes in, right?
Hold up, I have a question. It's a good one, actually.
Okay.
It's not a totally question.
No, you can ask your question.
You're talking
now.
about time and
Yes.
algorithms.
Yes.
What does that have to do with the graph?
Well, so basically, input size is x here, right? We could call it n, but I think that their variable is x.
So if I'm doing a sort, the x-axis is what?
So the x-axis is input size, and the
okay.
y-axis is time, right?
Got it. So when you were doing your trials last time,
some kind of vague estimation of time. We don't have to be too exact about it, but yeah, let's just call it time.
Okay.
So yeah, so this axis here, the y-axis.
So something's faster than something else if it's lower on the y-axis.
Yes. So the fact that this x squared graph, this 1/10 x squared graph, is beneath the f of x equals x graph, indicates at least that whatever algorithms they're describing, this algorithm is faster. From, say, input size 0, I guess, but we don't really care about that, to input size 10, which we might care about, right? Okay. But then if we zoom out, what happens, right?
De-enhance.
Yeah, exactly. Well, this is enhancing a different part of the graph, right?
Yeah, this is in BigO, I think.
Yeah, so out here what we see is that f of x cannot compete with x squared. X squared, if we're mathematicians, we would say it dominates x, right? And the reason why it does this is because as you go to infinity, you see that x squared is going to go to infinity a lot faster. And this is 1/10 x squared, right? We could play the same trick if we made it, say, 100th of x squared, right? Even if it's 100th x squared competing with x, eventually, right, x squared is going to, quote-unquote, win. If by win, I mean explode much faster. Yeah, in terms of
bad. This
right,
is actually bad.
In terms of algorithms, it means that it's going to take a lot longer. In terms of mathematics, we would say that x squared dominates x because as you go to infinity, basically the way to say it is something like this. Let me just write it down. And of course, you guys have all seen what limits are, so you'll love this. You'll love this little excursion.
Oh, I'm nervous.
Well, the good news.
I don't even have someone here to hold my hand while you write limit stuff. Oh,
actually, the good news is that. Well, that's very strange. Okay. Well, okay, so that is malfunctioning, so I will do something else. So basically, the limit
Are you drawing with your mouse now? Or?
Unfortunately, yes, because my tablet is on the wrong screen and I can't figure out how to fix it in 5 seconds. So, so if the limit of, say, g of n over f of n is infinity, then what we say is that g dominates.
You're doing very well.
I know, thank you.
Oh, you're right-handed. I'm terrible writing with a mouse because I use a mouse with my right hand, but I'm left-handed.
Right.
Yes.
You're mouse pedextrous.
Mm-hmm.
So, okay. So this is the general definition of domination. Cool. Okay. So let's talk about some other functions, right? So in this sense, what we would say is, at least what we would say is that x is big O of x squared, right? That's what we would say. And the reason why we would say that is why? Because eventually x squared gets bigger than x and stays that way forever. Right?
Mm-hmm.
So,
which means x squared is a bad algorithm compared to x.
That's true. That's true. Okay, so let's talk about some other functions. Let's talk about, let's say, y equals x cubed versus, say, x squared, right? And so we see that when we do this kind of thing, it's a little hard to see, so maybe what we'll do is we will...
Enhance.
Well, we want to adjust the x...
Enhancing?
Well, we're about to, dude.
Okay.
We want to adjust the x-axis.
I need this enhancement to happen.
Well, it's about to happen.
Okay.
So here we see generally what's going on with these two functions, right? So the purple is x squared, and the black is x cubed. And so what we see is that eventually x cubed is going to just grow much faster than x squared, right? And so we would say that if we're going to add to the list of things, x squared is big O of x cubed, right? Because eventually, basically the way to say it is eventually x cubed is going to beat x squared. And now you could say, well, what about if we attach some constant to it? If we say, let's boost up x squared by a factor of 50, right? Give it a better chance of winning. You know what I mean?
Mm-hmm.
Here we go. So there it is. And now we see, oh, look, it looks like x squared is winning, right? Looks like it. Is that really true, though? Let's test it out. Let's go out to 100. Ooh, wow, look at this. We have to go out even farther. Oh, wow, look at this. Okay. Maybe what we should do... Okay, 50 unfortunately makes it very hard to see. I'm not sure exactly how to show this on a graph. I think we might have to...
Can't you constrain the x-axis?
Well, yeah, I was going to do that again. So let's see here. Let's make it -1 to, I don't know, 200. And so we see that up here, eventually, right, x cubed is going to cross over x squared again, even after you attach this constant onto it.
It's going to get him.
And so, and kind of if you've taken enough calculus, which... you should basically know this already, right? Because if you take x cubed and you divide it by 50x squared, right, what are you going to get? Right, we're going to get... And let's hope this works this time. I don't know why it's on the wrong monitor. I can't seem to get it over.
I had those troubles the other day.
Yeah, let's see if...
You could just move this screen to the other monitor, right?
I could. Well, the problem is that I have to display the blah 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 and blah 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 blah. Let's see what this does. Nothing. Display capture 2. Here we are. Now we're on this screen. So basically what we would say is that if you take like, okay. If you take the limit of...
Are you back in pen country?
Yeah.
Oh, nice.
Of, say, x cubed divided by 50x squared, then what we're going to get here is, first I want to complete those x's, is we're going to get, just like every good calculus teacher does, the limit, as n goes to infinity, of x divided by 50. And so here's the thing. You don't really have to know very much to... Oh, wait. There should be x here. Or there should be n. One way or the other. Using the wrong variable. You don't have to know much about calculus or anything.
That was... hold on. I have to take a moment to appreciate how slick you were in xifying your n.
Oh, you don't think I've ever made those kinds of mistakes on a blackboard before?
I don't know. It was... Woo! You're like a tattoo artist who fixes bad tattoo art, but it's instead of art, it's math, and instead of tattoos.
I've seen the show, so I'm with it. So the point is here, right? As x goes to infinity, I don't really care what 50 is, right? 50 is some finite thing, and x is going to blast off to infinity. So the answer is that this is definitely going to be infinity, regardless of whatever constant we put down here, right? If we just put some constant c down here, it's really not going to matter. So, all right, cool. Okay, so let's transition back to the other... Okay, so that's enough of that. So let's talk about things that go better, though, right? So we've talked about x... Well, okay, so one last thing that goes terribly. Let's change x squared to 2 to the x, right? And here we see that 2 to the x absolutely crushes, right? X cubed. So basically, what are we learning? We're learning that exponentials dominate polynomials. But what... And then we have kind of the linear function, which is kind of a boundary case, right? So what performs better than linear functions, right? So let's talk about that for just a second. So basically, so what I'm saying here is this. I'm saying that currently what we have...
So exponential 2 to the x is like the final boss of slowness and badness, right?
Yeah, so we have lines, technically of degree bigger than or equal to 2, or bigger than 1, or whatever you want to say. And then what we also have here is, I guess I should put less than but not equal to, exponentials. The pen is acting really weird. I think some driver must have updated or something. Something is funky.
Have you tried unplugging it and plugging it back in?
You know, unbelievably, I have not. I don't know. Is this it? Let's see. See, it has a weird shape, too. It's like this diamond shape, and I'm like... Where did that come from? Things are going very strangely. Anyway, so what other kinds of functions are there in the universe? Yes, 2 to the x was used specifically because you see that vast majority of the time in programming. But you might even see stuff like 3 to the n. It's possible to write something that's algorithmically a 3 to the n. So, okay, so what is better than a line, right? So let's look at things that are better than lines. So let's graph a line. So the purple thing will be a line. So now we have to reset our, there we go. Why don't we try the square root of x? Now, what about squirt of x? So here, oh man, don't even get me started. As it turns out, lines and circles are the same thing in various geometries. But anyway, so we see here that the purple is x, and the black is the square root of x, right? And so we see here that square root of x, and as it turns out, if we did something like cube root of x, maybe x to the 1/3 power, woo, is actually going to also be under a line. So in terms of being functions, they're going to lose, but in terms of being algorithms, their time is going to be less, so they're going to win, right? Okay. And then our favorite function, which we have to talk about. What's the favorite function?
Everyone loves it.
Get ready, people.
It's big, it's heavy, it's wood.
Oh,
Better than bad, it's good.
it's a log.
It's log.
So there are some things that you might want to eventually learn, like log stands for log base 10. And so in computer science, I wonder if they actually have modeled this. No, they have not. So I wonder if they've just done it like log base 2 of x. Oh, that kind of worked. But who cares? Let's get rid of that because that's blurking everything up. So as it turns out, log is kind of our example of the, let's just call it the fastest algorithm that we're going to talk about today, other than maybe constant time algorithms. So log will beat everything. So basically the way to say it is that here we got roots, and then here we got log.
And log grows exponentially slowly.
Yeah, that's so. And why does it grow exponentially slowly? Because the definition of log is the inverse function of the exponential, right? So, however fast exponentials grow, logs grow that slowly. Okay. So, let's talk about big theta and big omega. So, what should we say about big omega, Ben? Maybe that it's the lower bound, right? It's the opposite of big O.
Yeah.
So, if big O represents an upper bound of a function, then big omega is the lower bound of a function. So the right.
When you say a function's big O, you're saying big O of some other function. You're saying that, or if you
Maybe we should just write. Yeah.
Big O of another algorithm, that means you're always going to perform faster than them after some point. And if something's big omega of another algorithm, you're always going to perform slower than it after some point. It's like the opposite, basically.
Yeah. So another way to say it is basically like if f is big O of g, then what that means is that f is at least as fast as g. And then the other thing to say is that if f is big O of g, then G, right, is big omega of F. And the reason why is because eventually G is going to be bigger than or equal to F, which is the definition of big omega. So big O is the upper bound, and big omega is the lower bound. All right. Cool.
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 That's very cool.
Yeah, so, and then of course let's define big theta.
Let's define it. It's big, it's theta, it's beautiful.
So, okay, so let's ignore what I just said there. And so let's just say that big theta is the asymptotic type bound. So I should not say those words. So basically, big theta is what happens when it's both big omega and big theta, right? Because big O has a less than or equal to sign, right? So F is less than or equal to G. Or I guess I should really say some constant times G. And this one says that G is bigger than some constant times F. And then the last thing to say is that when something is big theta, it's both. So what that means is that there is some constant A. So let's just write F is big theta of G, means that there's some constant A times G, which is less than or equal to F, which is less than or equal to B times G. And all of this must be put under the safety catchword of eventually.
And this is a big point. This is a big point. Guys, this is a big deal. So, like we said, if F is big O of G, then that's sort of like saying F is less than G. And then if we say F is big theta of G, that's sort of like saying F is greater than G. And if we say F is big theta of G, it's sort of like saying that they're very close. Basically, they're sort of equivalent in asymptotic.
I think one of the best ways to say it maybe is that something is big theta, and let's get rid of all this crap here. So something is big theta when you can stick it into bands. So let me show you what I mean by that. Like, let's say that we have 1/2 of x squared, and let's make another function that is, say, y equals 2x squared, right? Or let's just make it x. So let's make it 3x, and let's make this function x, right? Then we can basically say that y is equal to, say, 2x plus 5 is big theta of x. And the reason why is because there's a constant that you can multiply x by so that you'll get less than it. And there's a constant you can multiply x by that you're greater than it. And so you see here, this black function is the theta function. And the reason why it's the theta function is because there is this like band between this multiple of x and this multiple of x, and this function just kind of sits in there. And of course you have to say eventually after this intersection business, which is, you spend all your time finding intersections in algebra. We don't care. What we care is eventually this function kind of sits between these two functions. And then once it gets between these two functions, it stays there forever, right? So that's kind of the idea here. And you can do the same thing. It might be a little harder to see maybe with x squareds or something. So let's make something 3x squared. Whoa, 3. And then let's make something 2x squared minus 5x plus 1, right? And so our goal here is to kind of see that the black function is between these two functions. Now, it's a little harder to see, so let's adjust the domain again.
adjust your set.
Not just any set, man. Yeah, it is a lot like the squeeze theorem, actually. If you take the limit, of all these things, then you're essentially doing squeeze theorem stuff. Yeah, I mean, you can also say that it's an intermediate. Yeah, so those are both ways to say it. And so here you see that actually this black function, the one that we want it to be between, is not between. But here it crosses at this nice little intersection point. And then here, this is where it starts being inside the band of the purple function on top and the green function on bottom. And I mean, you might have to take it on faith, or you can just evaluate the limit, or whatever you want to do. But you will know that this thing eventually will stay between these two functions forever, right? It'll never get bigger than this purple one, and it'll never get smaller than this green one. Therefore, what can we say? We can say that this rando-looking function, 2x squared minus 5x plus 1, is big theta of x squared, right? Because there's a constant that makes it bigger, there's a constant that makes it smaller, and we can shove the one that we actually care about, this thing that we got here, in between the two. All right? You think that's a decent, what do you think, Ben? Good, bad, and different?
Yeah, when we're talking about the performance of algorithms and we use big theta, we're basically saying if one algorithm is big theta of a function or big theta of the performance of another function, we're saying they're like equivalent.
Yeah, exactly. We're saying that they perform what should we say? Equivalent kind of as you go to infinity. Yeah. As you make the sample, as you make the input sizes really big, they will start kind of performing like each other eventually.
In terms of this kind of analysis, they perform equivalently, even though they might not perform equivalently in terms of other kinds of analysis. But that's for much later, talking about other ways to analyze.
All right, so this has been as much math as I think anyone can handle.
Woo!
So let's do a little bit of actual like computer science. Mm-hmm. Right, so let's look at the swap function and try to figure out what kind of what kind of asymptotic complexity it has. And so, well, what kind of asymptotic complexity does it have? Right? So what does this function do? Right? So we look at it and it takes a list. The list is of size n. And so this swap function is just going to take the thing in slot I and slot j and swap them, right? It's not even doing any safety checking on I and j, so who cares? So how many operations is it doing?
7.
Oh, very good. Very good, 7. Also, I mean, maybe we can call it 3 for now. Right? I mean, it depends on exactly what you mean by an operation, right? So maybe what Ben means is that it requires you to look up a spot in RAM and then copy that thing. So actually this equal sign could be 2 operations. This equal sign could be 2 operations. And maybe you even count the function call as an operation. So
I was just saying a number.
Well, we got to 7. We got to 7 that way.
We did.
And actually this is the greatest way. So this is the greatest way to kind of introduce the point of BigO is, you see, I'm going to say that there's 3 operations here. Ben says that there's 7. And so the great news is that our answers are the same. Right?
Yep.
Because, as it turns out, if all you care about is up to a constant, then is 3 big O. My God, why this pen? Something has happened to it. It's like
this is what it does to me. This is what Liveboard does to me.
Oh no, this is not what Liveboard does in general. This is like some weird glitch of this pen right now. Anyway, well, because it's on the wrong monitor. It's doing all the wrong things. I think the wrong driver's taken over or something. It's like doing some funky stuff.
Oh no! Oh no!
So is 3 big O of 7? And so the question is there a constant, right, that we can say 3 is going to be less than or equal to a constant times 7 eventually? Well, in this case, the answer is yes, right? Because we can set that constant to be 1. And so, as it turns out, 3 is big O of 7. But now I'm going to ask the real tricky question, is 3 big O of 1? Right? And so the answer to that is actually yes as well. And why is that, right? Because is 3 less than or equal to some constant that we get to make up? We get to make this up. We get to invent this. Times 1. And the answer here is also yes. We can just say c equals 4, right? So now 3 is less than 4. So as it turns out, 3 is big O of 1. So this is why what we will say is that in case of like an algorithm that takes a constant amount of time, and so what do I mean by a constant amount of time? I don't care if it takes 3 steps or 7 steps. This algorithm always takes the same number of steps, right? Always. It never does anything different and always takes the same number of steps. Therefore, the swap algorithm is what we would call a constant time algorithm, right? And so because it's a constant time algorithm, we would say that it has big O of 1. Now, saying that it has big O of 1 does not mean that it takes 1 step, right? What it means is that it takes the same number of steps every time.
Regardless, so a list, the first parameter here could have a million. That list could have a million things in it, and you're still only going to do a fixed number of operations. You're going to do the same number of operations if it has a million things in it than if it has 12 things in it.
That's exactly correct. The size of the list, right, doesn't matter here. So this is a constant time algorithm because it takes the same amount of time. And of course, you might be a little worried because like maybe if it's passing in a bigger list or something, it has to do something different, but we know that that's not the case, right? It just looks up whatever's in the I position, it looks up whatever in the J position, and then it kind of swaps them in and out of the temp variable. Yeah, so generally you'll call the size of your list the parameter n. Cool. Cool.
Very cool.
I know, it's the coolest. So let's move on to find max. What is its time complexity?
Ooh. It might be more than 7.
It's probably more than 7. So here is my find max, right? So if the list exists, it returns the max. It just does a for loop, else it returns none. But let's look at the for loop, right? What has to happen in this for loop? So it takes the thing at the first index in the list, and then this is the key, right? It goes through the list, and it says if the list at I is bigger than the current max, then it sets the current max equal to the list I, right? So if we just look at this if statement, right, how many steps is this if statement? Well, who knows? Let's just call it 2, because it's 2 lines of code, right? But if we look at this for loop here, how many steps is this?
2.
Oh, not quite, right? How many steps does the for loop do, right? And the answer is, it does however many steps are in the list, right? So if the list is of size 2, then Ben is, of course, right. If the list is of size 10,873,241, then Ben is slightly less right. You know? So...
it's close, though.
I mean, yeah, very close. Both things are finite numbers, so it's essentially the same. So anyway, yeah, so basically the idea here is that this thing, and the if statement up here is, say, 1 step. This return statement is, say, a step. This return statement is a step. So, okay. So how many steps does this function take, really? Well, so what we're going to do, let's count it. let's see. You know what I could do? Ooh, beautiful. I could do this. I could, no, not that. I could do this. Crap. Let's do, this is working out less beautifully than I expect.
Just do
that.
Do
Is
Windows key Shift S, and then you could loop it and then drop it into your.
This is what I want.
Drawers. Okay.
This is what I want. I am doing what I want. So you can
then
see the function, and you
you're
can
living your
see.
best life.
Oh crap! I have to move them all to the other screen because of the glitch. Okay, let's go. Let's go, everybody.
Let's go out to the kitchen. Let's go out to the kitchen. Let's go out to the kitchen.
And now you can see this random number that I computed. I don't even know what that number means.
It's a number.
Yeah, you know, as it turns out, numbers are numbers. Okay, so you can see the function and you can see the steps. So what I'm going to say is it has to evaluate this if statement. So it's going to take one step there, and then it's going to set the current. Let's pretend like it's going to go into the if statement. So it's going to set the current map. So that's another step, right? And then it's going to go through this for loop. So it's going to go through the for loop n times, right? And let's say that there are 2 steps here inside of the for loop. So we say 2, right? Because each time...
2. See, I was right.
Yeah, no, I mean, of course you were right, Ben. Eventually the answer is always 2. And then it's going to return the current max. So that's one more step. So let's talk about what this algorithm really is. So of course you would say, okay, so this algorithm f of n is represented by, say, 2n plus 3, right? Probably, maybe. Or alternatively, if it goes through this if statement, then it's like maybe 2 steps, right? Or 2. So, I know, you're very happy whenever the number 2 occurs. So, okay. Let's think about what we can say about this. So what I'm going to say is that this algorithm is big O of n, right? Now, why am I going to say that? So because, well, 2n plus 3 is big O of n. And so why is that the case, right? It's the case because we get to choose the constant, right? So all we need to do is show that 2n plus 3 is less than or equal to some constant times n. Well, what constant can we pick? So it can't be 2 because 3 makes it slightly bigger. But can we pick the constant 3, right?
Yeah.
Yeah, what if we make c equal to 3? So the question is 2n plus 3 less than or equal to 3n? And the answer is yeah, because if you think about it this way, the 2n, this is really 2n plus n, right? And so what ends up happening here is that this 2n is going to equal to this 2n. So this 2n here is going to equal to this 2n here. Yeah, 2n is the loneliest number. But then the only thing we have to say is that eventually n is going to beat the number 3, right? Well, n is heading off towards infinity, right? So the point is that n is going to get to be, you know, a billion or a trillion or 10 to the 10 to the 10 to the 10, right? And so those numbers are presumably larger than 3. So this inequality is true. Therefore, it's big O of n, right? And so you see that you can kind of ignore, like, big O ignores this constant value here, and it ignores the lower order thing here. So we always call things of lower powers and lower things, we call them of lower order. So this is a lower order term that's getting ignored. Yeah, 2 or 1 can be as bad as 2. Yeah. Let's see if I can, whoa. Yes, perfect. Okay, let's make a new page.
I have a. I'm gonna say, well, I think it's big O of n squared.
Oh, you think it's big O of n squared?
Yeah.
Is 2n plus 3. Whoa. Beautiful. I don't know how it copied that thing. 2n.
Get this arrow. Arrow.
So Ben claims this. And I actually agree with him for once.
What?
Yeah, we usually disagree on a lot of things, but I agree with him now. Because he's speaking true facts.
Giving you facts.
That's right.
Spitting truths.
So here's the thing to think about this, right? So why is this true? And it's true because 2n plus 3 is less than or equal to, say, some constant c times n squared. And you might be like, oh, crap. I don't really know how to do this bounding operation. This algebra is really hard. I don't know. But what I do know is that eventually n times n, right, is going to be bigger than n. I know that because I'm multiplying by another n. So if n is, say, 100, then 100 times 100 is 10,000. If n is 1,000,000, then 1,000,000 times 1,000,000 is 1,000,000,000. So this is definitely going to be bigger. I mean, technically you can put like a little equal sign if you're going to allow n equal to 0 or 1 or something like that, but who cares? Really what we're just going to say is eventually, right? The true mathematician amongst you might actually say, but wait, if you select n is equal to 1/2, this is actually not true, which is why I'm saying eventually. So don't say that. Okay. The other thing I can say is that n squared is also bigger than 3. Also eventually, right? And it doesn't take long for that to happen, right? Because all I have to do is say plug in n is equal to 3. And all of a sudden, n squared is 9. And once I plug in anything larger, it's going to work. So I can basically pick the same constant. Technically, I could pick the constant 1, but I could even be very lazy and just pick the constant c to be 3. And so then I get that 2n plus 3 is less than 3n squared eventually. And so that's why this is true, right? Cool. All right.
So then why don't we just say everything's big O of 2n, or 2 to the n?
We could, but the tradition...
The proud tradition.
Well, the tradition is that you want to basically pick the smallest growing function to say that f is the smallest growing function g, so that f is big O of g. And the reason why you want to do this is because, yes, it's true that 2n plus 3 is big O of, like,
That O has a nose.
2 to the n, or whatever horrible super exponential function you can think of. But the thing is that this doesn't tell us anything, right? Like, this thing is so much faster increasing than this function that it doesn't, like, this thing is garbage. Right? The smallest function we can pick is n. If we pick the square root of n, then it's no longer true. But if we pick n, then it works, right? So 2n plus 3 is big O of n, but 2n plus 3 is not big O of, say, the square root of n, for instance, right? Because eventually 2n plus 3 is going to grow bigger than any constant times the square root of n. So the answer to your question, Max, is yes. No, the other way. So if f is big O of g, then g is big omega of f. Okay, let's talk about omega for just a second, because, we talked about it. So remember that the algorithm performs in either 2n plus 3 time, right? Or if it goes the other way and it just returns none, it performs in 2 time, right? So what big omega should we use to describe this algorithm? And so the answer is, we're going to describe this algorithm as big omega of 1, right? And the reason that we're going to do this is because all we need is that 2 is going to be bigger than or equal to some constant times 1. And the answer is that constant can be basically anything. It can be 1. Well, it can't be anything because it can't be 100,000, but it can be 1, so it can be the nice simple answer. And so I wish it would draw that extra thing. Okay, so there we go. Happy face. So we see here that, so it's this. Now, why is it not, right, big omega of n, right? Why is it not?
Why is it not?
Why is it not? Well, what that's going to require is that 2 has to be bigger than or equal to some constant times n, right? Eventually. And so the problem is, whatever constant we pick, even if we pick a constant of 1 over 1,000,000, right? If we pick n to be, say, 5,000,000, then we see the problem, right? Yeah, go ahead.
When n's greater than 0, its performance won't be 2. It'll be 2n plus 3.
Yeah, but who cares? I mean, what is the performance of this code? You know, it's either this one or it's this one. So it's true that this thing is big omega of n, but the smaller one isn't. So we can't say the whole algorithm is big omega of n, right? Basically, all I'm saying here is that 2 is not big omega of n.
That's true.
I mean, 2n plus 3 is definitely big omega of n. And remember that because it's big O of n and big omega of n, 2n plus 3 is actually big theta of n. Right? Okay. Right. All right, I think we've like analyzed the find max algorithm to its absolute limit, wouldn't you say?
To the depth of its limits.
Did you get the pun? Dial up that gronometer, dude.
Yeah, get the groaners going.
Yeah, exactly. I haven't been checking the gronometer.
They keep putting it at 6. They keep trying to get it to average out to 69.
Guys, this needs to be a scientific survey of the actual true level of groaning in the class. This cannot just be some stupid joke over and over. Come on, people. Let's do it. Let's do it right.
We just have to show them a graph. That way they won't have a number that they can make a ha-ha giggle number.
Yeah, I mean, I did say a pun, which means that, you know, my execution has been scheduled. Okay. So let us, let's see. Let us go back to the other display. Ooh, look. There we go. You can see my desktop background. What movie is that from, everybody?
Weekend at Bernie's?
Incorrect. Though close. Very close. So, here's the like primitives version of bubble sort without the like special checking. So let's analyze how this works, right? This is just the whole point of analyzing this function is not to analyze bubble sort because we don't care about bubble sort. The actual point is to analyze this function because it has some for loops in it, right? I mean, if we're being honest.
Are we being honest though?
Yes, this time. I tend I don't know why, but I tend to be honest when I lecture. Though I do tend to also believe that honesty is the worst policy. So, you know.
I disagree. Honesty is my favorite policy because it lets me be lazy.
Yeah, Uh, well, without going too far into it.
Yeah, we get in our big philosophical debates. People don't want to hear that. They want to hear about bubble sort.
No, they really don't. I'm sure that, like, if we polled, they would vastly prefer to hear us debate this. So, anyway, but that doesn't mean anything. That means we're going to continue doing this lecture.
Yeah.
Because, as it turns out, the Eighth Amendment does not apply. So, this is kind of a simplified version of bubble sort. What we see here is that it has two for loops, right? What does it do if we kind of analyze the number of steps? Oh, Max. Yeah, so does objective truth exist? Who knows?
I mean, that was okay. Yeah, we're not going to get sidelined by objective truth. And
I mean, the sad fact is that it just depends on your definition of objective, which probably just means that objective truth doesn't exist just because it depends so hard on the definition of objective. QED. See, that was the simplest way to hammer philosophy people down.
yeah,
I've only thought about this question for, 20 years now, so... Anyway. So, let's talk about steps. Can I make this bigger? Nope. Okay, so you guys are just going to have to deal with the tiny bubble sort. Oh, that's a great way to say it, too. It's tiny bubble sort. So, okay.
Can I show you a trick? Can I show you a trick?
Oh, what trick?
Have you done shift Windows key S?
Shift Windows key S. Yeah, I'm doing it now. What does it do?
Now drag a box around your bubble sort code.
Yeah? Okay.
Okay. And then paste and then do Control V in your live board.
Oh.
It's a screen grab.
Oh, okay. Anyway, that didn't work. So, whatever. Apparently it didn't paste the image. Who cares? Let's just keep doing like we were doing. So, what is the number of steps? And now I'm back to writing with the mouse because I'm lazy. So, what is the number of steps here? The number of steps is, well, whatever we do, we have to return. So that's one step. Awesome. And whatever we have to do in this for loop, how many times is that going to run? Drumroll please, Ben. Right? It's going to run n times, right? Because n is the length of the list. And then the question is, what happens inside of this for loop? Big parens. Well, it's going to look at this thing, and so how many times is this going to run? You know?
2?
Yeah, sure, it's going to run 2 times. So it's going to go up to the length of the list, right? So how many times is that going to run? It's going to run technically n minus 1 times, which is awful. And then, of course, I drew n plus 1 rather than n minus 1 because I'm, you know, Bolshevik traitor. I'm a Trotskyite. So, okay. So it n times runs n minus 1 times, and then finally we have this if statement, which is going to run 1 time, plus, let's say that swap takes 3 steps, maybe 4 steps. 3 steps, who cares? So the total function here for the number of steps, and I think by the end of the lecture you're going to see why we prefer to say big O than actually counting the number of steps, right? The whole point of big O is so that we don't have to do this silly process that I'm doing right now, right, Ben?
Agreed.
Okay, so then we have 1 plus, and then it's going to be 4 times n times n minus 1. And so now the question is, what is that the big O of, right? Or
N to the 2.
right. So you're going to claim. So let me just write this in a different form. 1 plus 4. Okay, so actually it's worse than that. It's 4n squared plus minus 4n minus 4n plus 1, right? And so, is this big O of n squared? Right? That's our goal. In the end, we want to just say that it takes n squared steps, right? Times some constant. And so, is it big O of n squared? And the answer is going to be yes, thank God. And so, why is it that way? Why is it just 4n squared minus 4n plus 1? Why is that big O of n squared? And so, I guess the answer is that eventually this thing is bigger. Oh, I'm sorry. This thing is less. Oh, wait. No, this is the easy one to do. This thing is just less than 4n squared. Right? Eventually. Because we have this nice minus sign, right? So basically, it's easy to just say 4n squared minus a bit plus 1, which is not going to counter this bit that we subtracted off, is definitely going to be less than 4n squared, right? So that's going to... Definitely. So that's going to be our constant c. And so that's the answer, right? Is that 1 plus... So it's definitely O of n squared. So the nice thing about this is, in real life, you're not going to count the number of steps in your algorithm, right? What you're going to do is you're going to basically look at this thing and you're going to say there's a for loop that runs n times. Inside a for loop and inside of that, I should say, is another for loop that runs about n times. And so overall, that's going to be an n squared algorithm. Yeah, I mean, yeah, so we can even do the big omega calculation of it too. Let's do that. Why not do live board? Why do not? Okay, let's try again. Am I online?
I got you.
Okay. Let's just load it up again, because it won't click to the new board, new page, which is making me kind of there we go. Perfect. So now we want to say the same thing. We want to say that 4n squared plus nope, not plus. Get rid of that plus. Minus 4n plus 1 is, right? Whatever this is means. Big omega of n squared, right? Yes, it would be the same. So, what are we going to do? Right? What are we going to do? Well, let's talk about it this way. So, is n squared, some constant times n squared, which we can probably just define to be 1 in this case, is some constant times n squared less than or equal to 4n squared minus 4n plus 1. And so the secret is that eventually one of these n squareds is going to be bigger than this n, or bigger than 4n's. And so basically what we can do is we can even bound this below by like 3n squared probably, but if we want to be mega safe, we can just do 2n squared is less than or equal to 4n squared minus 4n plus 1. And so that's really it. So what does that tell us, right? What that basically tells us is that this is the great way to say it. Let's just do it this way. What am I gonna do? Yes, here we are. Let's actually do the thing. So what happens if we just do a time test on, say, bubble sort? And let's do it. Okay, I don't even know what's running. It's definitely not this file.
Are you bubble sorting against bubble sorting?
Yeah, I'm just racing bubble sort against bubble sort. Um, so let's run one test of size 100. There we go. Okay, let's run. Okay, cool. So that finished in about 0.0009 seconds, right? Okay, let's do it again. Let's run a test, but now this time we're going to run it on a size of 1,000. Now, here's the thing about it taking n squared time. Whatever time it took, right, on that sample, we should expect that this will take approximately 10 times or 100 times as much time, right? Because 1,000 is 10 times 100. But the algorithm runs in n squared time, right? So the algorithm is actually not going to take 10 times as long with 10 times the size of an input. It's going to take 100 times as long, presumably, right? That's what our guess is. Let's see if that happens. Wonderful, right? Because before it was like 0.0009, and this is about 100 times that, right? It's a little more than 100 times that, but it's about 100 times that. Does that make sense? Is that this one took 100 times, essentially, approximately, 100 times as long to sort as the thing of size 100.
Yep.
So let's try it again. And so what's 100 times that? It'll finish in the class time. So I want to run one test on size 10,000. And so how long will this take? If that took 0.1 seconds, let's estimate.
10 seconds?
Oh yeah, that is 100 times 0.1
seconds.
Oh, 11 seconds. 11.
I was close.
You were close. So
it's because you're running all that fancy processing in the background, calculating the things that you do.
yeah, so I'm actually not sure why it's a little bit super quadratic, but whatever. It's more or less quadratic, right? This is tracking pretty well with a quadratic function, right? Because we estimated it would take 10 seconds. It didn't take 5 years. It didn't take 3 seconds. It didn't take 0.02 seconds, right? It took about 10 seconds, and that was our guess. So that's the power of BigO. BigO tells you, as you increase your size, is there a way to measure actual operations rather than seconds? Yes. You can measure it in actual operations. There's counts of operations. BigO doesn't measure operations. BigO measures quote-unquote algorithmic steps, more or less. Is that like a fair way to say it? Is that like it's a way to kind of guesstimate how many steps something will take, so that if it's running on 2 different computers that compile code in 2 different ways and actually have different operations, it's not dependent on that. It's only dependent on exactly how many quote-unquote steps there were in the algorithm, which kind of is fixed, but of course that's why there's the constant, so that it's fixed up to the constant. Okay. Does each algorithmic step take the same amount of time? The answer is not necessarily, right? Because if you increase the size of the list in this case, the list of size 100, right, takes a certain amount of time, but then the list of size 1,000 takes more time, right? Does he mean every step takes the same amount of time? Yeah, we kind of just pretend that's the case.
Pretend that's the case, and it's one of the short. So algorithmic analysis is we'll say it's coarse grained in the sense that it's if something's like if we're doing asymptotic analysis, if something's asymptotically faster than something else, it's way faster, like way faster. When things are in the same sort of class, like you have 2n squared algorithms or 2n algorithms, one can still consistently outperform each other because there's a bunch of things.
There's a constant. There's a constant sitting in the BigO too, which kind of secretly hides the differences between different n squared algorithms, right? One can be like a quote unquote 10n squared algorithm. One of them can be a 2n squared algorithm that'll go a lot faster. But BigO hides all of that.
Yes, Max is correct. It is an orders of magnitude thing. So if an n squared algorithm is is way worse, way worse than a n algorithm.
Yeah, I think the way to describe it is kind of it's the XKCD astronomy. Let's see.
Yeah, it's sort of a scale thing.
Like, yeah.
Your house is orders of magnitude larger than an ant, and your state is orders of magnitude larger than your house, and your country is an order of magnitude larger than your state, and the planet in order to, and then it's like zooming in and out of performance.
Yeah. I mean, basically, it's
But you could still have someone's house be way bigger than yours, but not be state-sized.
basically we're doing cosmology here. So, sometimes we kind of get into the engineer approximations in this comic, but most of the time, BigO feels the most about like cosmologist approximations because, in fact, pi is BigO of 1, and it's BigO of 10. So actually, it's even more true than Randall says here.
Yeah.
Anyway. So, how'd you think this went? Was this a good lecture, bad lecture, indifferent?
I think it was as bad as they usually are from us.
I think it actually went okay. I'm gonna give it a B plus, maybe a B, yeah. B plus.
Yeah.
Solid B.
There was math and I survived, so I think that's pretty good. It's kind of like there's any landing that you can walk away from is a good landing. Any math lecture you survived and stayed awake through most of the time.
Yeah, I mean, I kind of agree. You can't grade yourself. I can definitely grade myself.
Yeah.
I don't think you understand how this works. 7.5 out of 10. Damn, that's harsh. Damn. That's like mid C. I give myself a B. So, I mean, anyway.
Oh, C minus. Ouch. Ouch.
Or maybe we should just say, I don't know if I can find it this quickly. Oh, this is even better. Oh, I hope I can find it. Oh, I found it.
I give your invention the worst grade imaginable. An A minus minus.
There we go. Perfect. I got it. See, I found it. Incidentally, guys, the lecture's technically over now. Lecture terminated.
This semester, you only need a C to progress to 202 for this class. So, people have been asking that question. You just need a C this semester, and you get to go on to 202. However, that comes with a massive caveat that if you get a C this semester, you're still gonna have to get a B next semester in 202. So if you really felt like this class overwhelmed you and you might not be prepared, you might still want to consider taking it again.
Yeah,
it would be a very difficult to make that decision.
Because I think the one argument in favor is that if you get a C in this class, you have to kind of ask yourself the question, because I think we can be honest and say that we are going to try to give people grades that are kind of mimicking our standard thing. So if you master Python, you get the A. If you do well enough that we feel like you should progress to 202, we will probably try to find a way to get you the B this semester, right? I think we can. This is a vague enough statement that I think we can say it without any legal repercussions. On the other hand, if you get the C, then it's not that you are not capable of progressing to 202, but I think the general meaning of that statement is that we have doubts as to whether you will go into 202 and succeed. And given the doubts that we have, it's difficult, because I understand that most students are going to want to progress immediately. But if you don't progress, you should consider retaking. Even if you can because of the C. I think the way to think about it is that you only get 2 times to retake a class. Taking it and getting the C this semester means you can go on regardless. But if you take it again, then you'll at least have the strong enough background so that you don't have to take 202 twice. Maybe that's a way to say it. It's delicate because, we don't want to say, what if your Python is spaghetti but works and you get your projects done in 2 to 4 days? Then that sounds like you're going to head into a nice solid B if your Python's truly spaghetti. But I don't know.
Yeah.
But I mean, like, I'm just making that up.
All right. Well, I gotta go on to my next thing.
Yeah.
It's a pleasure as always. And next time we're gonna really seal the deal on this.
Next time on asymptotic analysis, I think really all we have left is like binary search, maybe one of the n log n sorts, and then we can talk about like something else.
Then we'll talk about what goes on beyond.
Yeah. Then we'll do like maybe some Flask or some.
Yeah, some Flask.
Tkinter.
Tkinter, some VPython.
That's right. Whatever we feel like. Crazy.
Yeah.
Literally crazy.
We're gonna do so much Python.
That's right.
That's right. All right. Bye, everybody.
All right. We are signing off.
Signing off.
That's what happens.